Hi everybody. Today our lesson is putting it all together. So we will be connecting the concepts we've been studying to the graph of an actual function. I just want to remind you, we're just using these methods to help us understand how the function, the information we get using calculus connects to the function itself. Use your calculator whenever we need to visualize the curve. And there'll be times in calculus when we don't want to graph the function, but we still need to obtain information about a function. And graphing helps us see that these values we get are justified. All right, so we're going to start with our first example here. If we're given this function, f of x equals x cubed plus 3x squared minus 9x plus 5, and I ask you to find the critical values, the relative maximum and minimum points, etc. Okay, as I look down on this ditto, I see that I'm going to be using the first and the second derivative today. So up top here, I'm just going to go ahead and find each of them so I have them handy and I can just use them when I need them. So this would be 3x squared plus 6x minus 9. And then working off my first derivative, my second derivative becomes 6x plus 6. So now I have these and I can just use them whenever I need to. If I want to find the critical values and the intervals where this function is increasing and decreasing, I know I'm going to be using the first derivative. And to find the critical values, I have to take the first derivative, and I'm going to set that equal to 0. Remember, this is your first derivative. In order to find the zeros of this function, I know I'm going to have to factor. Okay. This is stuff you have to know on your own. I could divide away the 3, that doesn't matter. And I would have x plus 3 and x minus 1 equal to 0. So the critical values for this function are x equals negative 3 and x equals 1. Okay. Now this is a polynomial function, so I only have to worry about this type of critical value. I'm going to put them on my number line. And notice I already have my number line set up for me. So I have negative 3 and 1. Okay. Now we need to test each interval. Now these are steps I expect you to know. I'm going to pick a number in each of these intervals, and I'm going to plug them into the derivative function. Now I like to use the form I use to set it equal to 0. That's the easiest one that I can do in my head. So if I take a number in each section and plug it into the factored form, I should get my signs for up above. I'll give you a few seconds to take care of that. If you want to pause the video for a moment, you can. Negative, f prime is positive. Positive, negative, f prime is negative. And when x is greater than 1, I get positive, positive, and back to a positive interval. And what does this tell me about my original function? It means my function is increasing, then decreasing, then increasing again. So if I want to describe these intervals, I can say my function is increasing negative infinity to negative 3 and 1 to infinity. My function is decreasing from negative 3 to 1. Now I'm going to move on to my maximum and minimum points. Okay, notice I'm being asked to describe points, so I want to get the x and y value for each maximum value and minimum value if there are any. So my maximum values I find from when the critical value is 0, and the maximum is when I go from a positive to a negative. Notice if you put your arrows, you can kind of see it. So my maximum value occurs when x equals negative 3, and my minimum value occurs when x equals 1. And if I want to get this value as a point, I'm going to plug negative 3 into my function. And whatever I get as the answer, that's going to be the y value of my point. To get the minimum value, I'm going to plug 1 into the function. And whatever I get as my y value, that's going to be the point on the curve. Now I did go ahead and do this workout. I did this workout for you. So if you want to, again, take a few seconds, work that math out on your own, you'll find out that when you plug in -3, the y value is 32. And when you plug in 1, the y value is 0. Remember, these are points on the actual function itself. Now moving on to our next step, we want to find the intervals of concavity and any points of inflection. So when I do concavity and points of inflection, I'm going to go ahead and use the second derivative, which I already found above. My critical values are going to be found when I set the second derivative equal to 0, and that occurs when x equals -1. Okay, so I'm going to go ahead and I'm going to put -1 on my number line. I'm going to pick a test number in each interval. By now, I'm assuming you all these steps are second nature to you. When I plug -2 in, and again, I'm using this function here. If I plug -2 in, I'm going to wind up getting a negative. And if I plug a number bigger than -1, this interval is positive. So now I know my function is going to be concave down, and then it's going to switch to concave up. I can describe my intervals of concavity. My function is concave up from -1 to infinity. My function is concave down from -infinity to -1. And since this value, this test number, so to speak, right? We don't call these critical values anymore. This is a test value, but because I got it by setting the derivative equal to 0, I should actually have a point of inflection here, and I'm going to find that point of inflection by plugging -1 into my function. When I plug -1 into my function, I wind up getting a y value of 16. Therefore, the point -1, 16 is a point of inflection on this curve. Okay. Now we're going to go ahead and we're going to sketch this curve. Before I do, this is going to seem a little weird, but bear with me. I just kind of want to go up top here, and let's kind of break up this grid into some of the important places on this graph. Now, if you look here, in this section, when x is less than -3, my function is increasing in concave down. Then I'm decreasing in concave down. Then I have this point of inflection. I change from decreasing to concave up. And then my graph goes increasing and concave up. Remember, this was your max. This is our min. And this is our point of inflection. Now we're going to plug this function into our calculator and see if we get a picture that kind of looks like that. And this is all I expect you to do, is sort of see. So I have my function in my calculator, and when I go to graph it, it's hard for me to see, so I'm going to adjust the windows. Again, I don't necessarily expect you to be able to know this stuff, but follow along with me and just watch what happens. So I'm going to adjust my y value so I could see a better picture. And if you notice, it sort of matches what we came up with over there. Now, if we were truly graphing this, we would go on and find x-intercepts and y-intercepts and all that other stuff. But this is just a sketch. So I want to point out some of the things I'm studying right now which are my maximum values, my minimum value, my point of inflection. Again, notice it's not perfect. And does it connect to what we've been studying or the information we got from above? It sure does. Increasing, concave down, decreasing, concave down, decreasing, concave up, increasing, concave up. So that's what I would like you to practice tonight. We're going to do one more example together. Okay, that example is going to be a rational function, and then I'll let you be on your way. Now, the hardest part of this is actually getting the first and the second derivative. I want to save time, so I'm just going to give you the answers. The first derivative here is the work for it. The first derivative is 2x plus 1. I'm sorry, 7 over 2x plus 1 squared. And the second derivative at negative 28 over 2x plus 1 cubed. Okay. Now this work, again, I expect you to be able to do on your own, so we're working off of things that you already should know. If I want to find critical values and intervals where the function is increasing and decreasing, what I'm going to do there is look at the nature. This function is a rational function. So when our derivative is a rational function, we have to remember, we have to set the derivative equal to 0, find where the derivative is undefined. And now I want to point out to you that if you go up into the original function also has issues. X can't equal negative 1/2, okay? Right, that's going to make the original function undefined. And what we know about a rational function, this is going to be an asymptote, okay? So it's going to be kind of something we have to think about as we move through this problem. Where is the derivative equal to 0? Well, that does not happen. Where is the derivative undefined? So I'm going to take 2x plus 1, set that equal to 0, right? That's the denominator equal to 0. Solve that equation. The derivative is undefined when x equals negative 1/2. However, x equals negative 1/2 is not defined in the original. So technically, this is one of those weird values. There are no true critical values for this function. However, we still have to consider what's going on at this x value. Something's happening there. Take a number less than, a number greater than, test them in your derivative. Now this one again, super easy. Doesn't matter what kind of number you plug in. The numerator is always going to be positive, plugging into the first derivative. The denominator, no matter what you get, if you square it, you're going to have a positive value. So this function is increasing over the entire domain. Except we've got this weird thing going on here, right? Trouble. That's all it is. It's just a little weirdness. Now, relative maximum and minimum points, well, the only place that could occur would be here. And since it doesn't change signs and there is no actual point, there are none. Don't worry about that. Talking about intervals of concavity and any points of inflection, now we're going to go ahead and we're going to take and analyze our second derivative. It's a rational function, so I have to look to see if there's anywhere where the second derivative equals 0 or the second derivative is undefined. Set the numerator equal to 0, set the denominator equal to 0. Doesn't happen. Here, if I cube root each side, I get 2x plus 1 equal to 0. Again, my My test number is -1/2. But this is not a true test number, although we still will put it on our number line. I always do that to remind myself. I can't have a point. It's a weird thing. When I tested my second derivative, this one's pretty easy to test in too. My numerator, since there's no variable on top, is going to be negative. And then when I take a number less than -1/2, inside I get a negative. If I cube a negative, I get a negative, so this interval is going to be a positive, which means this section is concave up. Over here, if I take a number that's bigger than -1/2 and I cube a positive value, this section is going to be concave down. And again, remember, here's where our behavior, here's where the significant behavior changes may occur, is going to be right there. Before we move on, I completely forgot to describe the increasing and decreasing intervals. I know you think this is not important, but it is. This function is increasing for all the numbers, except we've got an issue here. So if we're going to describe this as intervals that are increasing, we have to break it up, because this is a broken up interval. Nothing, I don't have an answer when I plug in. So I would have to describe my intervals of increasing like that, and decreasing there are none. If I go back down here, my graph is concave up from -infinity to -1/2, concave down from -1/2 to infinity. And will there be a point of inflection on this curve? Even though it looks like it, remember, if you plug in -1/2, you don't get an answer. So even though it changes concavity, there is no actual point of inflection. Okay, these are some of the weird things that we have to try to clear up in our early days of calculus. Now we're just going to go ahead and make a general sketch for this curve. Now again, I want to remind you, there is more to sketching. But since we're just kind of seeing that the calculus is reinforced by, what we're studying is reinforcing each other with the graph, we're not going to get too crazy. We're going to plug our function in and just see that things match up. So if I go to graph this function, okay, again, I'm going to have horizontal asymptotes, I'm going to have vertical asymptotes, and if you notice here, our vertical asymptote is occurring at -1/2. I have a horizontal asymptote somewhere here. I could get it real easily by determining the end behavior. So I know just by looking at my function that my horizontal asymptote is 3/2. But what I really want to point out to you is if you sketch in this curve with what you see from your calculator, it goes something like that. It's not perfect. I want to just show you how it matches up. The graph of my function is increasing and concave up. The graph of my function is increasing and concave down. And that pretty much correlates to what we see in our picture. Okay, so even though it seems like we did a lot today, it's really just connecting some of our concepts. I just want to make one more note before I leave you to do your homework. I will not be asking you to sketch by hand on the test, but it is good to see the connection. Please make a valid attempt on your homework. So long.